Absolutely all galaxies, except for our own, are extremely distant astronomical objects. We will never truly know what happens in these immense gravitationally bound systems and the stars within them. Unfortunately, I will never have the chance to visit them. We can't send an umbrella or any device there. We won't know if there is life or wondrous forms of life. The universe, unfortunately, has taken away that possibility from us because colossal distances separate us. Galaxies are scattered throughout the entire universe. Nevertheless, we are grateful since one of these galaxies once gave us life, and now we observe them since time immemorial. Still, we can't lose our desire to study them. However, to be honest, the nature of these objects has long eluded our understanding. Each of the galaxies is currently living its own life cycle. They collide, merge with others, evolve in their unique way, die, and are reborn. Each of them is distinct and peculiar. Almost everything you know about objects in the universe, planets, stars, moons, nebulae, is located within galaxies. They have become a peculiar haven for everything. Today, we will talk about the existing galaxies, their varieties, and the secrets they hide. To start, it's worth noting that the number of galaxies in the observable universe is genuinely unknown. However, with the naked eye, we can see 4 whole galaxies in the sky. They are the Andromeda galaxy, the Large and Small Magellanic Clouds, and the 33 galaxy in the Triangulum constellation. But despite being able to see the contours of galaxies clearly in the sky or in photographs, in reality, galaxies do not have clear boundaries. It is not possible to precisely determine where the galaxy ends and intergalactic space begins. In the optical range, a galaxy may appear to have a certain size, but when measured using radio observations of interstellar gas, its radius can turn out to be much larger, and this is not uncommon. Typically, the size of a galaxy is understood as the photometric size, which is represented as a certain curve on its illuminated surface, connecting points of equal brightness. The measured mass of a galaxy will depend on its size. But for a clearer understanding of what we are talking about today, let's touch upon the main components that make up the structure of galaxies. Firstly, there is the core. The core is a small region at the center of the galaxy. When we talk about galaxy cores, we often refer to active galactic nuclei, where processes cannot be explained by the properties of stars concentrated in them. In such cores, processes occur that release an enormous amount of energy. Common signs of activity in these cores include the ejection of ionized gas or high-powered radio emission, though not always. Often, the unusual behavior of active galactic nuclei is associated with supermassive black holes, and currently, this is the most widely accepted theory. The second component is the galactic disk. The galactic disk is a relatively thin layer where most of the galaxy's objects are found. It is a component in the lens of visible and spiral galaxies, containing spiral arms. The disk predominantly contains younger stars compared to the galactic bulge, and their motion is well ordered. They revolve around the center of the galaxy in nearly circular orbits lying in the same plane. Galaxies have a high density compared to their surrounding physical components, like the halo or bulge, which are populated with older stars. In the disks of galaxies, often, spiral arms can be observed, radiating from the center of the galaxy, where the density of interstellar gas and young stars is particularly high. It is within such a spiral arm that we live, and from there, I created all this graphics and assembled the video for you. Next, let's talk about the so-called galactic halo, a term used in astrophysics. The galactic halo is an invisible component of a galaxy and is hypothetical in nature. Essentially, the galactic halo is the outermost part of the galaxy that greatly interests scientists, as studying it can help understand where the gravitational influence of one galaxy ends and another begins. The galactic halo is a rather intriguing element, and I will likely cover it in separate videos. Another galactic component is quite rare and is known as the polar ring. For example, the galaxy NG 4650A has this component. In the classical case, A galaxy with a polar ring has two disks rotating in perpendicular planes, with the centers of these disks coinciding. However, the exact cause of the formation of polar rings remains incompletely understood. Galaxies with polar rings are a type of galaxies where an outer ring of gas and stars rotates over the poles, and these polar rings are believed to form when two galaxies interact gravitationally with each other. The next galactic component is called the bulge. It is a central bright elliptical component of spiral and lens-shaped galaxies. It mainly consists of old stars moving on elongated orbits. The typical population of the bulge includes red giants, red dwarfs, or supernovae, two types, as well as variable stars like Cepheids or globular clusters. For example, in typical lens-shaped galaxies, the bulge is larger relative to the galaxy's diameter compared to spiral galaxies. In my opinion, the bulge is one of the most interesting elements in the structure of galaxies. There's also the so-called pseudo-bulge, but that's a topic for another time. Now, let's talk about the bar, or in layman's terms, the bridge. It looks like a dense and elongated formation consisting of stars and interstellar gas. It serves as the primary supplier of interstellar gas to the center of the galaxy. With this knowledge of the necessary components, we can now move on to classifying galaxies and learn more about these stellar islands. There are different classifications of galaxies, such as the Hubble classification or classifications based on infrared telescopes. However, we won't choose a specific classification today, but simply discuss the particular characteristics of each type of galaxy. Let's start with elliptical galaxies. Approximately 25% of all known galaxies are of this type. They are highly luminous and, from a distance, appear like giant shining spheres with the highest brightness at the center and fading towards the edges. Elliptical galaxies are nearly entirely composed of old stars, giving them a yellow or reddish hue. New stars are almost not formed in them since the amount of interstellar gas and dust in them is negligible, although there are occasional exceptions. Elliptical stellar systems differ only in size and compression. They are classified based on their compression with letters E from 0 to 7. This number corresponds to the degree of flattening of the system. For example, a 0 would be a spherical cluster, while E6 would be much more flattened. Moreover, according to the classification, an S0 galaxy can be perfectly round, while an S7 galaxy can be oval-shaped. The star formation in galaxies of this type has ceased for several billion years, and there is hardly any cold gas or cosmic dust left. Most massive galaxies are filled with very sparse hot gas with temperatures over 1 million kelvins. On the other hand, in spiral galaxies, which we will discuss after elliptical ones, star formation occurs more uniformly. Therefore, the most massive stars in elliptical galaxies have long completed their existence, while in spiral galaxies, new stars are constantly being formed and observed. One of the most common examples of an elliptical galaxy is mighty. Spiral galaxies are the most widespread type and probably the most beautiful. They constitute more than half of all known galaxies. A spiral galaxy appears as a disk with a bright yellow ball in the center, around which spiral arms are coiled. These arms consist of fainter branches with a bluish tint due to the presence of specific stars, such as white and blue supergiants. In contrast to elliptical stellar systems, they possess several distinctive structural features. Firstly, spiral galaxies have spiral arms where active star formation processes occur. Secondly, they have a stellar disk, which is a relatively thin layer of matter along the galaxy's plane, where the main mass of objects in the system and stars is located. Stars within the disk rotate around the center of the galaxy. In spiral galaxies, the presence of interstellar gas and dust, essential for star formation, is widely observed. Many spiral galaxies have a peculiar structure at their center, known as a bar, from which the spiral arms extend. They are classified with the letter S and differ in the density of arm placement. Typically, these galaxies have 2 or 3 arms, although in some cases the arms may vary in size. All of these arms, unless influenced by galactic collisions, are coiled in the same direction around the center of the galaxy where most of the matter is concentrated, such as a supermassive black hole and dense spherical clusters of old stars, known as bulges. For instance, our own galaxy, the Milky Way, and the Andromeda galaxy, which we will inevitably collide with in about 4 billion years, are both spiral galaxies. The Sun is located between the arms, away from the galactic center, and its velocity of movement is approximately equal to the rotation speed of the arms. This positioning allows the solar system to avoid dangerous regions of active star formation, where supernovae often occur. It is worth noting that spiral galaxies are often observed beyond galaxy clusters. They differ in the degree of development of their spiral structure, which is denoted by adding letters A, P, E, B, or C to the SS symbol. Galaxies with a have the main number of stars concentrated in a central bulge, while the central branches of the spiral structure are weakly developed or just indicated. In galaxies with B, the branches are more developed, and for those classified as C, the branches are well developed in galaxies classified as C. The main number of stars is contained in heavily developed and often scattered branches, while the central bulge has relatively small dimensions. The most well-known spiral galaxies include our Milky Way galaxy, the Andromeda galaxy, and the Bode's galaxy. An intermediate type between spiral and elliptical galaxies is the lenticular galaxies, classified as cirro. In galaxies of this type, there's a bright, highly compressed central bulge that resembles a lens, while the arms are either absent or very weakly traced. Lenticular galaxies primarily consist of old giant stars, giving them a predominantly reddish color. They differ from elliptical galaxies because they have convexity and a thin disk, but they are distinct from types A because they lack a spiral structure. The main population of such galaxies comprises old and massive stars, mostly of red and yellow colors. 2/3 of the lenticular galaxies, like elliptical galaxies, do not contain gas, while in 1/3 the gas content is similar to that of spiral galaxies. Consequently, star formation processes, though present, occur at very slow rates. An example of a lenticular galaxy is the Spindle galaxy in the constellation Draco. More interesting are the so-called irregular galaxies, which do not fit into either the elliptical or spiral categories. Irregular galaxies lack any of the common forms and are usually characterized by chaotic connections, stellar clusters, and sometimes lack a distinct shape or pronounced center. They are relatively rare and make up approximately 5% of the total number of known galaxies. The reason why irregular galaxies differ so significantly from their galactic counterparts lies in the likelihood that each of these stellar systems was likely once an elliptical or spiral galaxy, but something disrupted their formation process or structure, leading to their irregular appearance. Such galaxies are mainly divided into two types: those that have some resemblance to a structure, allowing them to be classified into certain sequences of galaxies, and those that do not even have a semblance. There's also a third type known as dwarf irregular galaxies, characterized by a low amount of heavy elements and a large amount of interstellar gas, making them similar to the galaxies of the early universe. Hence, studying this type of irregular galaxies is crucial for understanding the process of galactic evolution. Moreover, in these galaxies, one can observe young, hot stars. They contain a significant amount of dust that blocks much of the light from the star. It is likely that such galaxies have planets where the sky appears rather modest and dull. Personally, I would not recommend observing them through a telescope. Bright examples of such galaxies are Nisi 1427 or the Magellanic Clouds. As for the galaxies that possess certain characteristics but cannot be categorized into any of the aforementioned classes, they are referred to as peculiar galaxies. Their structural features can vary, such as distorted structures due to interactions with neighboring galaxies, the presence of dust lanes, ejections of matter, and so on. A classic example of a peculiar galaxy is the radio galaxy NC 5128T. In reality, Today, I have only covered 1% of what I wanted to discuss with you. Today, we have only familiarized ourselves with the essence of how these vast stellar islands are structured. In future videos, we will unveil the secrets of the most unusual, fascinating, and unique galaxies.
Andromeda Galaxy is perhaps the most well-known galaxy to the general public, excluding the galaxy we live in. This galaxy is frequently featured in science fiction works more than any other galaxy. This is not surprising because it is the largest galaxy closest to Earth. It takes about 2.5 million light-years to reach the Andromeda Galaxy, which is a surprising number for us, but a trivial distance in terms of the universe. The Andromeda Galaxy is one of the few galaxies visible to the naked eye. Therefore, its existence has been known for a long time. However, its structure cannot be seen due to the fact that it is very far away. Therefore, in medieval literature, it was depicted as a small cloud floating in the night sky. Even with the invention of telescopes, this problem could not be solved. Early telescopes were very primitive, so individual stars in the Andromeda Galaxy could not be distinguished. Some nebulae were discovered in the Milky Way, and the protagonist of this video was also considered one of those nebulae. The original name given to this galaxy was the Andromeda Nebula, due to such circumstances. In 1855, scientists noticed an explosion that occurred in the Andromeda Galaxy. It was probably a very bright supernova, but it was considered simply the new star starting to burn. The fact that a star begins to burn inside a cradle of stars, known as a nebula, was already known at that time. Therefore, this distant galaxy is constantly expanding. The misconception that common nebulae are impossible to understand seems to be deepening. It was only towards the end of the 19th century, when the telescope had been improved, that we were able to barely recognize the structures of whirlpool arms in the Andromeda Galaxy and bright nebulae. This was also around the time when a faint voice first suggested that what we were building was not a nebula, but another galaxy, like the Milky Way. However, at the time, the single galaxy model was dominant, and most scientists thought that the Milky Way was the entire universe. It should be noted that in the mid-19th century, there was a claim that the Magellanic Clouds were other galaxies, but many people denied it for the same reasons. To defend the scientists of the time, their reaction was not simply due to rigid thinking. At the time, astronomers did not have the ability to measure distances to distant celestial bodies as accurately as we do now. For example, in the case of the Andromeda Galaxy, various researchers estimated the distance to be closer to Polaris than the North Pole. Finally, in 1923, the great Edwin Hubble succeeded in using the latest telescope of the time to discover several Cepheid variables in the Andromeda Galaxy. Cepheid variables are a type of bright yellow variable star that has the characteristic of always changing its brightness with the same period, even though it is the same star. There is a formula for deriving the distance to a star by substituting the apparent brightness and actual brightness of the star. Cepheid variables are the easiest type of variable star to improve. When Hubble improved the distance to the Cepheid variables in the Andromeda Galaxy, he realized that it couldn't exist in the Galaxy 1 group. Even the boldest of the past calculations turned out to be wrong. The distance was over 2.5 million light-years. As a result, the scale of the universe known to humankind expanded enormously. Other celestial bodies, such as the Magellanic Clouds, were also confirmed to exist beyond our galaxy by Hubble. Andromeda Galaxy was the first to be identified as a galaxy. As research progressed, we learned many new and interesting facts about the Andromeda Galaxy. For example, we learned that this galaxy is much larger than our own Milky Way, with a diameter of over 45,000 parsecs and containing at least first-magnitude stars. The largest galaxy in our local group is the Andromeda Galaxy, followed by the Milky Way. Like the galaxy, Andromeda has a distinct disk and several spiral arms. Most of the countless stars that belong to the Andromeda Galaxy are included in this disk. The center of the galaxy contains the galactic nucleus. Interestingly, the galactic nucleus appears to be double. Even in photographs, two distinct structures, one large and one small, separated by about 5 light-years, can be clearly identified. The structure on the dimmer side is called P2, and it is believed to be the true center of the Andromeda galaxy. There is a supermassive black hole at this location, but its mass has not yet been fully determined. Estimates suggest that it may be tens of millions or even billions of times more massive than the Sun. For reference, the supermassive black hole at the center of our own Milky Way galaxy has a mass of only about 4.3 million suns. The larger and brighter structure, located slightly away from the center of the galaxy, is called P1. However, it is currently unclear what this structure is. Perhaps, from an astronomical perspective, relatively recently, the Andromeda galaxy may have consumed another galaxy, and that galaxy has not yet been completely digested. If that is the case, P1 may be the remnant of the disrupted galaxy. Even those who have never heard of it before may not know that galaxies sometimes swallow other galaxies. Andromeda is particularly interesting in this regard, as one of the highlights is the globular cluster called Mayall-2, which is located 130,000 light-years away from the galaxy's center. Mayall-2, discovered in 1953, is known as the brightest star cluster in our local galaxy group. Usually, globular clusters are composed of very old, dim stars that were born at a similar time. However, Mayall-2 is more interesting because it contains a variety of age groups of stars, including some that are much younger. Stars with a high metal content also exist. There probably isn't any life in the May star cluster. In the globular cluster, stars are always in planetary system shapes because they are densely packed. Nevertheless, rare shapes are clearly visible in the Andromeda galaxy that are smaller than formal galaxies, including dwarf galaxies. These structures have a spherical shape, a very large radius, and contain a large number of stars. Perhaps, like Mayall 2, they are remnants of swallowed galaxies. In 1999, scientists recorded an anomalous phenomenon called PA99 in the Andromeda galaxy. During this process, the fusion of an old red giant star, one of the observed low-mass celestial bodies, was caused. There are several interpretations for this phenomenon. Some scientists believe that this mysterious celestial body could be a planet with a mass of about 6 times that of Jupiter. If their view is correct, this would be the first extraterrestrial planet discovered in another galaxy. However, other astronomers argue that the object involved in this phenomenon is not a planet, but a small star. In any case, there will be many planets in the Andromeda galaxy, including those similar to Earth. In this galaxy, there are very old stars and very young stars, and the stars are clearly divided into 3 generations, accounting for most of the population of the galaxy when combined. Scientists paid attention to this point immediately. The age of these stars ranges from 10 billion to 11 billion years, respectively. Of course, what we are most interested in is the second star that corresponds to the Sun. There are enough of such stars remaining in the Andromeda galaxy, so surely many extraterrestrials will be discovered. If there are any intelligent beings or humans that still exist in the Andromeda galaxy in tens of billions of years, they may come to meet us without even having to show off their technological skills. However, the problem is that the two galaxies are slowly approaching each other and will collide and merge 4 billion years from now to become one galaxy. But there won't be any major cataclysms on the scale of the Earth. The distance between the stars is quite wide, and even if aliens interfere between us and Proxima Centauri, there won't be any significant harm. Please subscribe to our channel and press like, and don't forget to share this video on social media. Space is a place of frighteningly vast distances. Just the thought that incredibly fast light takes 13 billion years to reach us from some galaxy can make one feel uneasy. But if we focus on the positive, the distance between us and Mars, just a dozen or so light minutes away, seems like a hop in space terms. And there are times when our cosmic neighbors seem incredibly close. Even the 4 light-years to Alpha Centauri don't look scary compared to distant galaxies. It's insanely close, and there's no doubt that humanity will eventually reach our solar system's cosmic neighbors. But who are they, apart from Alpha Centauri? Few would name the stars neighboring our Sun, but don't worry, we'll cover that in the next couple of minutes, and also estimate how far away they are. Before we talk about the chances of finding life on our cosmic neighbors, let's first discuss how scientists can determine which stars in the sky are close to us and which are far away, and how they can be sure they're not mistaken. The concept of a parsec, which you've probably heard of from science fiction, is a unit of measurement that was introduced thanks to the use of parallax. The prefix par means parallel, and SEC stands for sector of gas, which is, of course, a joke. The actual meaning of acer is arcsecond, thanks to which we can use Apple devices to experience parallax in a simplified way. In fact, with the release of the iPhone 7, Apple introduced a new type of wallpaper that creates the illusion of depth when the phone is moved, simulating the effect of parallax. The term symbolizes the change in the apparent position of an object depending on the position of the observer. Try holding up your finger and closing your left eye while looking at it with your right eye. Then, quickly close your right eye and open your left eye. You should see your finger appear to jump to the side. This is the same principle that scientists use to measure the distance to nearby stars. If you move your finger closer to your eyes and repeat the procedure, you will see that it has shifted more than before. If you draw imaginary lines to your finger, you will get a triangle, one side of which you know well the distance between your eyes. The two angles at which the eyes are looking at the finger are also known, and finding the length of the remaining side, which will be the distance to the finger, is a matter of time. And now, put reason and great scientists, whole generations of hard work and huge formulas on this scheme, and you will get a method according to which the distance to the objects was calculated with excellent accuracy. Distances to thousands of stars, and even to the planets of our solar system, as well as the Sun itself, were initially determined using the parallax method. This method is based on observing how their position changes against more distant objects when viewed from different points or as the Earth rotates. It is not difficult to guess that objects that are too far away cannot be calculated using the parallax method, since we are limited by the diameter of the Earth. Even when viewed from both ends of the planet or during a complete rotation, the displacement of distant stars will be negligible. Other methods are used for those objects. But what we are interested in are the nearest neighbors of the solar system, which can be reached by simple parallax and later refined using more accurate methods. It should be noted that even 10 light-years is a huge distance. The distance is too great for us to judge the number of neighboring stars definitively. In order to determine the distance to something, you need to see it first, and among the stars, there are very dim brown dwarfs. Therefore, the question of a precise number of our nearest neighbors remains open at the moment. With brown dwarfs taken into account, it is estimated that there are 14 large neighboring stars at a distance of 10 light-years from our solar system. Let's start our story with a tiny red dwarf, standing at a height of 154. If we were to send light directly towards it, it would take about 9 69/100 years to reach it, which is amazing. At least we know that this star is still alive, unlike some fairy dish that sent its light to us about 6,000 years ago. We see it as it was when the ancient Egyptians were building the Pyramid of Cheops, so what can we say about row 154? Not much. It's a very typical star, as red dwarfs make up more than half of the stars in the galaxy. Row 154 is 5 times smaller than the Sun in mass and 300 times dimmer in brightness, and is located in the constellation Sagittarius. Despite its proximity to Earth, it cannot be seen with the naked eye. Interestingly, 154 is characterized by intense X-ray radiation, which is greater than that of the Sun. This can be explained by the star's relative youth, as it is less than 1 billion years old. At the time of its formation, there were already algae on Earth. However, due to its proximity to the Sun, the star falls into the first category of astronomers' attention. Searching for planets around stars is incredibly difficult because they are very dim compared to stars, and 154's height itself is not particularly bright, plus it is close. At one point, one of NASA's missions was very interested in studying this star because theoretically, we could find a planet there that is 3 times the size of Earth. However, unfortunately, funding was not obtained and there wasn't much reason for the planet, which would need to have Earth-like conditions, to be located 4 times closer to its star than Mercury is to the Sun. Its orbit would be blocked, and the hypothetical Earth-like planet around 154 would always be facing one side, receiving too much X-ray radiation and too little red light for photosynthesis. Therefore, even theoretically, finding habitable planets around red dwarfs like 154 is extremely challenging. We don't really have anything to do with our lives, but our theories are still based on the Earth, so let's talk about Sirius instead. You don't need to get to know it twice, it's the brightest star in the night sky. If you put the Sun and Sirius at the same distance, Sirius will be 25 times brighter than our star. However, we shouldn't be deceived, there are much brighter stars in space in absolute terms than Sirius. For example, Rigel's luminosity is about 120,000 times higher than the Sun's. If you were to switch places between Rigel and Sirius in the night sky, Rigel would shine like a third of the moon. Nevertheless, Sirius is still a bright star. It is roughly twice as heavy as the Sun and almost twice as large as the Earth, so it has been known to humans since ancient times. It was worshipped in ancient Egypt, Babylon, and Greece, and that's where it all started. The name Sirius, which translates as shining, also refers to its location in the constellation Canis Major. According to legend, Sirius is the dog of Orion. The Romans even translated the star's name as Canicula, meaning little dog, because its morning visibility coincided with hot days, which later became known as dog days thanks to the star. Now, the word vacation is associated with the meaning of the word canicula, and school children all over the planet are happy to have it. What is this neighbor, located just 8.5 light years away from us? Sirius is a great star of spectral class A1, and it has a tiny white dwarf companion, Sirius B, which astronomers jokingly call the puppy. This is really the case because Sirius B is 360 times dimmer than the Sun. However, it should be noted that there are much brighter stars in space than Sirius in absolute terms. Puppy is still well-fed, and in terms of mass, it is not inferior to our Sun, being one of the largest white dwarfs. However, this does not make the Sirius system particularly unique. There is every reason to believe that systems with 2 stars are more common in space than single stars, and our introverted Sun is a typical resident of the universe. If there is potential for life in this system from our point of view, then a terrestrial planet and conditions for liquid water would need to be located far from Sirius, as far as Jupiter is from the Sun, which is 4 times farther than the Earth is now. The year would last about 6 years, which is not the worst thing, but the worst is that Sirius emits much more ultraviolet radiation than the Sun. It is possible to forget, and therefore there are questions about ordinary free oxygen, and the weight of the Sirius puppy will also affect the orbit, and therefore the stability of conditions on the planet. In general, everything is very bad, and from the point of view of real research, even worse. Sirius is very bright, and despite its proximity to the Sun, it is very difficult to find a planet near it. Current scientific achievements allow us, in theory, to find only a planet with a mass of 510 Jupiters at a distance of 25 times farther than the Earth from the Sun. In 2008, such a test was conducted, and the result was predictable negative. Some scientists still believe that Sirius is not a binary triple star, and we still cannot conclusively refute them. Hubble tried to find another brown dwarf or some huge Jupiter, but he could not, although the theoretical calculations as a whole allow for the possibility of stable orbits within the system. Perhaps in the near future, we will study Sirius better, as it slowly approaches the Earth, and in the next few tens of thousands of years, it will shine even brighter. However, the distance will increase again, but we can say for sure that for another couple of 100,000 years, Sirius will be the brightest star in the sky, unlike our next neighbors. Wolf 359 is an insanely dim red dwarf. It is closer to us than Sirius and is located 7.8 light-years from the Sun, but much dimmer. It is impossible to see a planet with the naked eye in the sky. If we were to switch our Sun to Wolf 359, then Earth's round shape would disappear. Without a telescope, it wouldn't be visible, and during the day it would be 10 times brighter than during a full moon on Wolfie 359. We wouldn't have stopped if it weren't for its high cavity in two directions. The first reason is the potential presence of two exoplanets. In 2019, a team of astronomers led by Meg Kotlamy published a study announcing two candidates for exoplanets in the Wolf 359 system. The planet is 20 to 40 times larger than Earth and rotates twice as far away. The second planet is allegedly only 4 times larger than our planet and is located close to the star, close enough to allow the possibility of life. However, scientists quickly cooled their enthusiasm, as the amount of radiation that this hypothetical planet would receive would be many times greater than Earth's, making the existence of life unlikely. The planets themselves are still only candidates, as direct observation and confirmation of their existence is difficult. But scientists remain interested in Wolf 359 for two reasons. First, this star is located near the plane of the ecliptic, which means that if you were to look at the Sun from the Wolf 359 system, all the planets of the solar system would be visible at once. Hypothetically, if advanced aliens have scattered probes throughout the universe for scanning, then a probe on Wolfie 359 could easily discover the existence of Earth. And, in turn, by observing Wolfie 359, we may find a hypothetical probe studying us. Of course, these searches have not led to anything yet. Much more productive to scientists is the legendary star Barnard, another neighbor of our Sun. It is the second closest object of its type to us, or the fourth if you count Alpha Centauri, which is a triple star system. Firstly, it is important to know how fast Barnard's star is. It approaches us so quickly that it creates the impression that it owed the Sun 100 kilometers. Except for the Sun itself, it is the fastest star in the sky, flying towards us at a speed of 110 kilometers per second. And if now Barnard's star is somewhere 6 light-years away, then in 11,000 years of our era, the distance will be reduced by a third and will already be equal to 3 whole light-years. By cosmic standards, this is insanely fast. We see it as it was at the time when the construction of the Pyramid of Khufu in ancient Egypt had not yet begun. There is not much interesting to say about its height of 154, as it is a very typical star, since red dwarfs make up more than half of the stars in the galaxy. Its height is 5 times smaller than that of the Sun, and its brightness is 300 times less. It is located in the constellation Sagittarius, and, despite its proximity to Earth, it cannot be seen with the naked eye. The only notable thing about its height of 154 is the incredibly intense X-ray radiation it emits, which is more than that of the Sun. This can be explained by the star's relative youth, which is less than 1 billion years old. When it was formed, there were already algae on Earth, but because of its proximity to the Sun, the star is among the brightest in the sky. In addition, it has X-ray radiation and is a bit lazy and slow-moving old guy, but this doesn't negate the fact that the temperature on the surface of this star, belonging to the red dwarf Barnard, is almost 3,000 degrees. It's worth respecting at least because, due to its proximity, it has become almost a standard in studying stars of this type. It's quite difficult to study them because they are dim and heavy, but it's slightly easier to search for planets than it used to be. Peter van de Kamp announced the discovery of 2 planets orbiting Barnard's star in 1960. The first planet was similar in mass to Jupiter, while the second was only half as large. However, Peter couldn't find confirmation of his discovery, even though he tried very hard. The Hubble telescope helped to clarify that planets with a mass greater than 5 Earths cannot orbit Barnard's star. It seemed that there was no hope left, but in 2018, an international team of astronomers announced that they had found a planet about 3 times the size of Earth, orbiting Barnard's star at more than twice the distance that Earth orbits the Sun. However, despite the accuracy of the calculations, Barnard's planet B still remains a candidate, although its existence was also confirmed in 2021. Furthermore, most astronomers give a 90% chance of potential life on a potential exoplanet. However, even if the planet is twice as close to its star as Earth is to the Sun, it will receive extremely little heat due to the coolness of the star. Sometimes the temperature on a hypothetical exoplanet is unlikely to be higher than -170 degrees. In general, the prospects for life are bleak with the other neighbors of Earth that have potential for life. However, the mighty system of Alpha Centauri, consisting of 3 stars, comes onto the scene, located about 4 light-years away from the Sun. 2 of the 3 stars in Alpha Centauri A and Alpha Centauri B, are of great interest as they are very similar to our Sun. Alpha Centauri A shines 1.5 times brighter and is slightly larger than our Sun, while Alpha Centauri B is slightly smaller than the Sun and shines half as much. The entire Alpha Centauri system is slightly older than the Sun, and visually the 2 large stars merge into one when observed from Earth. This is not surprising since they orbit each other at an average distance of only 24 times the distance between the Earth and the Sun. If the Sun were replaced with another star, in moments of closest approach, the star would be separated by a distance equal to that between the Sun and Saturn. The third member of the star system, Proxima Centauri, is a true runt. It is only 1.5 times larger than Jupiter and is a red dwarf. Even Barnard's star looks like a giant against its background. Proxima Centauri is also actively studied, but it is the 2 older sisters, Alpha Centauri A and B, that really excite scientists. They have been studied extensively, even peering into their atmospheres and finding similarities to the Sun, and conducting some of the most precise calculations of possible planetary and life presence. Many simulations were conducted and they conclusively ruled out the presence of giant planets. This is not surprising since 2 of the 3 stars are so close together, and Jupiter would face a sad fate between their gravitational influence. However, simulations showed that both stars have a so-called habitable zone, which is an orbit where theoretically stable planets with liquid water can exist. Unfortunately, due to the brightness of the stars, even taking into account the insane proximity of the Alpha Centauri system, it is difficult to say anything. In 2012, European astronomers claimed to have found an exoplanet around Alpha Centauri B, but its existence was disproved 3 years later. The situation is slightly better for the larger star, Alpha Centauri A. In February 2021, a candidate exoplanet was found there that is remarkably similar in size and orbit to Earth. It will be verified by the James Webb Telescope, and we still have yet to learn the outcome. However, the true king in this scenario is quite unexpected. In the search for life, the collapse of the Proxima Centauri system is not surprising. On the one hand, as we mentioned before, it is slightly easier to find planets around dim stars. However, the exoplanet discovered there in 2016 is astonishing. It is also almost identical in size to Earth, but its year lasts only 11 days, which means it is much closer to the star. Considering that Proxima Centauri is a dim star, this is an ideal combination of factors. The exoplanet candidate receives 65% of the Earth's warmth, which theoretically opens the doors to the existence of liquid water. However, more recent calculations are less optimistic due to the proximity to the star. Potential Earth 20 receives an indecent amount of radiation, and since Proxima Centauri is a red dwarf, it periodically experiences powerful flares. For example, in 2017, a flare was recorded that according to scientists' data would have certainly killed the planet. All your life on a planet, even if one existed, is not so bad. There are several candidates for exoplanets in the Alpha Centauri system, some of which are also in the habitable zone. There is hope that the James Webb Telescope will help confirm or refute this data, but of course, Alpha Centauri is the main candidate for all organizations that aim for interstellar travel. There is, of course, the Project Daedalus, which aimed at the Barnard star, but this is rather an exception because scientists mostly dream about Alpha Centauri, and here dreams come up against harsh reality. Humanity has exactly one spacecraft that shows signs of life outside the solar system, Voyager 1, which was launched in 1977 and was actually designed for 5 years. It miraculously stayed on track and in 2012 entered interstellar space, but even it will not approach another star for 40,000 years, although it is not about Alpha Centauri. Voyager is heading in a different direction, as are the New Horizons and Pioneer 10 spacecraft. Their missions, like Voyager, were mainly focused on the inner part of the solar system. Specifically, nobody has sent anything to other stars yet. However, if Voyager had been turned around at the same speed and sent to Proxima Centauri, it would have reached it in 76,000 years. And mind you, this is one of the fastest spacecrafts in human history. Of course, there is also the Helios 2 probe, which was accelerated using the gravitational pull of the Sun to an indecent speed of 240,000 kilometers per hour. But even with this speed, it would take 19,000 years to travel 4 light years. There was a prototype electromagnetic engine from NASA that went even faster during testing. But even for it, it would take 13,000 years to fly to Proxima Centauri. Nuclear and thermonuclear reactor projects do not help much. They are either too dangerous, too expensive, or too slow. The laser sail technology is considered the most promising in the near future. According to this technology, a sail is deployed around the ship, just like in the old days, and solar radiation accelerates it for greater speed. This sail is pushed by lasers, and according to Robert Frisby's calculations, it could reach Alpha Centauri in 12 years. However, for this to happen, its diameter must be a paltry 320 kilometers, and the useful payload would be a canned food tin and a tennis racket. And there is also antimatter, engines powered by which can be incredibly efficient. However, the production of 1 gram of antimatter would cost several $trillion. Overall, the situation with interstellar travel is very sad. Either the necessary technologies don't exist yet, or they are just concepts, or they are too expensive, considering that interstellar travel has little practical value. It's clear that most scientists are focused on solving everyday problems. The bright spot on this background and hope for our generation is the Dragonfly project, which involves sending a very tiny sailcraft to Alpha Centauri. The goal of the project is to reach the star within 1 generation, but for now, it's just a concept. Strictly speaking, we need to study our own solar system better, and until we finally figure out Mars and potentially habitable moons of Jupiter, looking towards Sirius and Barnard star is premature. You may have heard that the Sun is an incredibly large celestial body compared to the Earth, but there are even larger stars beyond that difference. The biggest of the biggest. What I'm going to introduce now is a star named Stephenson 2-18. This star is located in the same constellation as the number 1 star that had reigned in the past in the constellation of the Shield. The Shield star was considered the biggest star ever, but later it was determined that Stephenson was even bigger. This star is the first part of the binary system Stephenson 2, and it is located about 18,900 light-years away from Earth. It has rewritten a few records not long after its discovery. As you may already know, Stephenson 2-18 is the biggest star that humans could imagine. If we placed this star in the position of our Sun, even Saturn's orbit would be within the star. 5 planets including Earth, which is closer to the Sun than Saturn, would be swallowed by this giant star. In addition, Stephenson 2-18 is also one of the brightest stars in our galaxy. According to IAU standards, its brightness is even 440,000 times that of our Sun, depending on the calculation. However, there are times when it shows a more modest figure of only 98,000 times brighter than the Sun. Nevertheless, it is still an unusually bright star. If the sun shone as brightly as this star, not only would we be unable to see anything, but the Earth would have been completely incinerated. Thanks to its abnormal luminosity, Stephenson 2-18 is visible even beyond the galaxy. If there were a civilization that developed somewhere in the Andromeda galaxy, Stephenson 2-18 might have been one of the first stars discovered by extraterrestrial beings using telescopes. This star is exceptionally cool in this category, classified as M6.0 on the spectral type. Its temperature is not even close to that of an advertising light at 3,200 Kelvin. Typically, stars classified as red supergiants are hotter and are known to have temperatures of at least 3,500 Kelvin. Originally, this star is also extremely rare. It is not a very high rating for a red supergiant. Moreover, this star is too bright compared to its rating, and conversely, its temperature is too low. Of course, it cannot be denied that there might be a possibility that scientists made some miscalculations somewhere. However, if there were no errors in the calculations, this peculiar star will throw a big shockwave to the current scientific models, especially to the models related to the evolution of stars. What does this giant star reflect? When talking about various rare stars, the public raises one question: can life exist in that stellar system? However, for today's protagonist, there is nothing special to discuss as no planet has been discovered yet. However, we cannot assert that there are no planets simply because we have not found any. Therefore, let's imagine what kind of planets could exist around this star and what possibilities there are. First of all, Stephenson 2-18 was not originally in its present state. We need to keep in mind that from birth, there are no red supergiant stars. Stars become red supergiants as they age, including our Sun, which will follow the same fate, although it won't become as massive as others. We don't know what kind of genius this star was before becoming a red supergiant, but it was probably a massive star with a similar spectrum to our Sun, and it would have remained in that state for billions of years, providing enough time for life to emerge on planets in its system. At that time, this star was not particularly large, at most 2 to 3 times the size of the Sun. Although it was not as bright as other stars, considering other characteristics, it would have had a relatively large and bright habitable zone. There may have been more than one planet within the habitable zone. In other words, there is a good chance that life existed in the Stephenson 2-18 system. There is a possibility that there are multiple planets with such conditions. In that case, what are the chances of discovering intelligent life by discovering a way to travel between stars and visiting the present time? Unfortunately, the probability of that happening is low. When this star began to expand and take on its current form, the planets inside the heavy-tailed zone would have been swallowed up. In addition, the brightness of this star has been increasing since long before that, causing the planet's surface to turn into a sea of lava. In other words, even if the planet itself still exists, all Earth-like life forms will have perished. However, there may be sharp viewers who raise a question here. As the star expands and becomes brighter, wouldn't the heavy-tailed zone widen? Moreover, even if a planet near the primary star was destroyed, couldn't a celestial body that was far away until now become one instead? When the binary system was young, the farthest edge of the star system was trapped in a hellish cold similar to Pluto in the solar system. However, after the star became a blue giant, the temperature rose and it became warmer. If there was sufficient gravity, there might have been the possibility of liquid water or atmosphere appearing there. However, there is one problem. The star's blue giant phase is an extremely short period in astronomical terms. It might be enough time for life to be born, but it would not evolve. Additionally, if there were planets in distant regions that had deep oceans under an ice cap like Europa and life existed there, it would be destroyed due to global warming. The ice cap would melt, and the oceans would become vulnerable to radiation from space. In other words, if there were organisms including intelligent life on Stephenson 2-18, they would not survive. Even if it existed, it seems that it perished a long time ago. At best, we can only assume that an intelligent life form moved to another star system with a longer lifespan. As I mentioned before, the fate of a star in its red supergiant phase is very short. As the star expands, it can no longer maintain the outermost layer of gas due to its gravity, and the gas is scattered into space. As the star's mass decreases, so does its gravity, which means it cannot retain a lot of material. The star cannot stop melting away, and eventually, it will become a white dwarf, leaving only its core. That's all for today's video. Thank you for watching until the end. I hope you enjoyed the video. To summarize, we are living in a perfect time to observe rare stars like Stephenson 2-18. By studying this star, we have learned a lot about the fate of other stars, including our own sun. Unfortunately, with our current technology, we cannot send a probe to explore this star, but we can still enjoy many other interesting events in space, including aliens. Please subscribe not to miss any of these interesting issues, and don't forget to like and share this video on your social media. We are also waiting for your comments on this video.
Just imagine an endless plain, and there's a descent covered by waves of an eternally restless sea. To all this, add extreme pressure levels and immensely powerful winds. The sky is completely covered by a dense blanket of clouds, and only in the distance does a red sun peek out on the horizon, just for a moment before hiding behind the clouds. Now you can barely see it. The sun doesn't actually change its position, but that didn't stop it from disappearing from our view. Look around. It seems like the last place where any living organism could exist. However, it's not that simple and straightforward. We have just described to you how the so-called second Earth on this planet could look like. Researchers may also start searching for extraterrestrial life forms. So, what kind of astonishing planet is this? We're sure that after watching our videos, you might have had the desire to work in the field of space exploration. However, remember that there's plenty of work to be done on Earth as well. As you know, in the last decade, scientists have discovered a huge number of exoplanets. Currently, there are 4,370 of these objects, located in approximately 3,230 planetary systems. Among them, around 3,000 planets are in the confirmation stage of being exoplanets. Typically, these objects are of enormous size, including gas giants, super Earths, and super Jupiters. Technical exoplanets are large bodies that orbit their stars in a relatively short period of time, making them much easier to detect than smaller planets. Exoplanets can amaze us not only with their sizes, but also with the possibility of hosting living organisms. The number of candidates in this regard is in the dozens, and they become a piece of home for researchers. Among such exoplanets, GJ 832 stands out. It is located in the constellation of Grus, and scientists believe that it has the highest probability of hosting life among all known exoplanets. The main star around which this object orbits is named Gliese 832. The distance between it and our Sun is approximately 16 light years. Gliese 832 is a relatively dim red-colored object with a luminosity of about 0.7 of the Sun's luminosity. The mass and diameter of the star are approximately 50 of the Sun's respective values. The temperature on Gliese 832 is around 326 degrees Celsius. Due to this, the habitable zone around the star is quite narrow. Objects within this zone will experience tidal locking, meaning they will always have one side facing the star. The most famous example of tidal locking is the Moon and Earth. It is known that there are two planets in the habitable zone of Gliese 832. One of them is Gliese 832, discovered in 2008, which has characteristics similar to Jupiter. Its mass is about 2/3 of Jupiter's mass. The distance between Gliese 832 and its star is approximately 3.4 astronomical units. In 2015, a second planet, Gliese 832 with an Earth Similarity Index of 0.81, was discovered. This is considered a high value and didn't go unnoticed by the global scientific community and, of course, sensation-seeking journalists. As a result, Gliese 830 acquired another name, Second Earth. However, despite these two planets sharing similarities, there are many differences between them. Nevertheless, the Earth Similarity Index of Gliese 832 is very high, and its mass is equivalent to 5.5 times that of Earth. The orbital period around the main star Gliese 832c is 35 Earth days. The distance between the star and the exoplanet is 0.16 astronomical units. It's worth noting that the distance from Earth to the Sun is defined as 1 astronomical unit. One peculiar feature of Gliese 832 is that due to its relatively wide orbit, it may occasionally leave the habitable zone. As a result, rapid temperature fluctuations are characteristic of this exoplanet. The amount of energy that Gliese 832 provides to the exoplanet is essentially equivalent to the amount of solar energy that Earth receives. The temperature on the planet itself reaches 20 degrees Celsius. It is assumed that the atmosphere of Gliese 832c has a relatively high density, which can increase temperature level. We have already mentioned the high probability of the exoplanet being in tidal lock-in with its star. Additionally, its habitable zone is relatively narrow, indicating a small distance between Gliese 832c and its star. Since exoplanets are always tidally locked to their main star, there are significant temperature variations between the illuminated and unilluminated sides. If the atmosphere's density is sufficiently high, storms can occur on Gliese 832. In the Gliese 832 system, there may actually be not 2 but 3 planets. Scientists from the University of Texas at Arlington concluded this in 2017. The estimated size of the presumed third planet is approximately 10 to 15 times the mass of Earth. It is located at a distance of 0.25 to 2 astronomical units from its main star. The existence of the third planet has not been confirmed yet, as more data is needed. However, let's return to Gliese 832. Let's imagine how this exoplanet would look if it had living organisms. The gravity level on Gliese 832 should be noticeably higher than on our planet. We don't know the exact diameter of the planet, so we cannot determine its gravity precisely. However, we do know that the density of Gliese 832 is similar to that of Earth, so its gravity could be approximately 3 times that of Earth. These measurements would contribute to the formation of a more even relief and the depth of oceans on Gliese 832. These conditions can be considered favorable for the emergence of living organisms, as there will be more areas where potentially warm water can exist. Regarding the appearance of Gliese 832, the most likely scenario is that the relief formations will be of a reddish color. This is due to the dim light and high atmospheric density. Because the exoplanet is in tidal lock-in, the unilluminated side will have high temperatures, while the illuminated side will have lower temperatures. There will be a ring-like region where the illuminated side transitions to the unilluminated side, and this area will have the most favorable temperature for the development of living organisms. Precipitation in the form of liquid water will be abundant at the boundary with the dark side, where glaciers would melt. As a result, the amount of water would increase. However, a significant drawback in this case would be the incredibly strong winds caused by temperature differences. These winds could be restrained by high mountain formations. However, due to the gravitational forces, these mountains would not be of sufficient height for that purpose. The exoplanet moves in an elongated orbit, but it is relatively small due to its close proximity to its main star. As a result, the change of seasons occurs approximately once a week when the exoplanet is closest to or farthest from its star. When it is closest, summer arrives, and when it is farthest, winter comes. The inclination of the planet will not play a significant role. It is the distance between Gliese 830 and its star that determines the season. It is presumed that in the ring-like region of the exoplanet, the change of seasons will have a similar effect as tidal forces on Earth, causing tides and periodic flooding of certain areas, followed by water receding. During these processes, particles of different substances enter the water, creating an ideal environment for the development of living organisms. Scientists suggest that life on Gliese 832c may thrive exclusively in a watery environment. The effects of gravity and temperature variations in the ocean are significantly reduced. Potential living organisms could adapt to frequent changes of seasons by migrating to more comfortable areas or entering a state of dormancy, making harsh conditions less of a concern for them. Now let's imagine how these living organisms, if they ever appear on Gliese 832 or have already started to appear, would look like. Plants, most likely, would resemble mosses and have a dark color to maximize their solar energy absorption. To withstand strong winds, they would need sturdy roots. Due to the high atmospheric density, there could be atypical forms of organisms that develop directly in the atmosphere rather than on the surface. They would move with the direction of the wind and extract necessary substances from the air for their vital processes. Of course, all these discussions remain mere speculation for now. It will take many more years before we can truly ascertain the truth of these assumptions. What do you think? Does the exoplanet Gliese 830 explain itself in such a way